The topic today is starting with the unanswerable questions. So what I primarily want to look at today is integration. Say, I thought we were done with integration. Well, integration of things that are, well, a little more complicated than we might normally think of. So let me give you a really simple example. I want you to calculate the cosine of x from 0 to 0.2. Let's say this is what we wanted to do. You'd say, well, this is not a complicated problem at all. I would say this is going to be basically sine x from 0 to 0.2, which is sine of 0.2 minus sine of 0, which is just sine of 0.2. Great. And as a decimal, because I really want a decimal value, if I'm in physics and I'm doing a measurement, or chemistry, I'm doing a measurement, this is the exact answer. This is what we want. This is a closed form answer, but I still probably need a decimal because I might need this many milliliters of solution, or this might be the amplitude of the sine wave, or it's something. So when I calculate that, first thing is always make sure you're in radian mode. And then I'm going to do the sine of 0.2. And my answer is approximately, whoops, that's a 0, sorry, 0.198669933. That's as much precision as my calculator is capable of doing. This is not a terminating decimal. This goes forever, but that's pretty good accuracy. You say, well, this is like day one of Calc 1 integration. You're right. This is day one of Calc 1 integration. So let's change the problem. Let's make it, I don't know, how about cosine of x squared? Now, I'm going to make a cosine of x squared. Now, I might be able to cleverly manipulate this. I might be able to cleverly manipulate this and in such a way that I can solve this. Or maybe I can't. You see, the argument here is not friendly because I don't have a chain rule factor. There's no 2x sitting here, and I can't create the 2x. So really the question is, can I even integrate the cosine of x squared? Can you think of a function that when I differentiate it will give me the cosine of x squared? Well, you might say, how about if we tried an integration by parts? Integration by parts actually would be the only way you could do this. Let me rewrite this, if it can be done. So I would probably do something like this. Now, you remember how we did integration by parts when you actually only had one function? Does anybody remember how we did that one? We integrated the log function. We integrated the inverse tangent.
You would pretend there's a 1 there, and yeah.
And so this would have to be my u, because I don't know its antiderivative. So I'd say let u be this, and then my dv would be 1 dx. Then my du would be the derivative, which would be negative sine. So I'll put the negative 2x in front, and my v would be, sorry, I need a dx there. Sorry, getting a little crowded here. And then my v would be x. So let's see the general antiderivative. Let's see if this actually will work. I love integration by parts because you can take problems that seemingly cannot be answered, and you can often, and that's the key word, often answer them, not always. Remember, there's a lot more integrals that cannot be integrated than there are that can. I know how to do cosine x, but cosine of thing, maybe not. So the general antiderivative would look something like this. Okay, so that'd be plus, and then I'd have the product, that'd be 2x squared sine of x squared dx. Now, can I do this one? Well, I'd do the same thing. I'd probably do an integration by parts again, but I think what we're going to get is an infinite loop here. We can do integration by parts. Remember, we can do integration by parts forever and ever and ever, but at some point, I want to have a statement that has no more integrals, so I have a finished answer. And I don't believe we can finish this one. I think we're dead in the water. So my original question cannot be answered. Well, I cannot give you a closed form. I can't say the answer is the sine of 0.2, like we did in the first case. I can't give you a closed form. But what if all you needed was decimal accuracy? In fact, let me go a step further. What if, okay, I don't need a closed form. I don't need an antiderivative, but I absolutely have to have at least the first 10 decimal places. Now think of that. I I can give you lots of decimal places, but that doesn't mean they're accurate. I need absolute correct decimal accuracy. Now, there's a common misconception when it comes to decimals that people confuse. Let me have some fun with you. Pi. Pi is 3.141592. That's as far as I actually know. 0.76388495. I've given you tremendous precision. Precision is the number of decimal places. But because I made up all the numbers after here, there's no accuracy whatsoever. Precision is how many decimals you report. Accuracy is that everything you reported is actually correct. In mathematics, what are we more concerned with, precision or accuracy? Say it. Anybody?
Accuracy.
Accuracy. We could care less about precision. That's up to the calculator. So when people are taking chemistry classes and physics classes, they'll tell you how many decimals. That means they're telling you the precision, but they want all of them to be correct. Oh, so if I said I want an answer that is accurate to 10 decimals, I don't care if you give me 1,000. I need the first 10 to be absolutely correct. Not that you just gave me a bunch of decimals, but that every one. Remember, when you're doing estimations, which you've done before, remember the tangent line leaving the curve. When you're doing estimations, you might report a lot of decimals, but none of them may actually be equal to the actual answer. So I want to make sure everybody understands that, because that's sort of the nature of what we're doing. On the last quiz that you just did, you gave me a Taylor polynomial. Let me see if I can find it. I just had it. Hold on a second. Where did I put it? We derived something. Oh, here it is. Sorry, I had it right here. We did a problem. And by the way, I'm apologizing for being a little bit behind on my grading. No good reason, except that I gave a discrete math exam on Monday, and there's a lot of people in that class, and I've been trying to finish that while grading. So I'm a little behind, haven't got all you guys's. So we did a problem where you used P3 of X, the third degree Taylor polynomial, to give a estimation. So technically what we'd say is this is, we had 1 plus 1/2 X minus 1 minus 1/8 X minus 1 squared plus 1/16 X minus 1 cubed. This was your third degree Taylor polynomial. Most people gave me this. It's beautiful. This is not equal. This would be an infinite sum. I'm just doing the first few terms. So then I said, now let's use our Taylor polynomial to do an estimation of, I think it was square root of 1.4. So the square root of 1.4, we're going to estimate with P3 of 1.4. This is P3. And when you plugged in the numbers, you got exactly 148 over 125. If I put a 1.4 in here, or think of it as 14/10, I'll get exactly that. And as a decimal, that's 1.184. So what we're saying is, using my third degree polynomial, this is the answer to the last question. Okay. This number's not very precise. I've only given you 3 decimal places. The question is it accurate? Well, I don't know that until I pull out my calculator, which I just, my goodness. Oh, here it is. I keep setting things on top of things. I'm going to take the square root of 1.4. Now, when I take the square root of 1.4, the calculator says the square root of 1.4 is approximately 1.1832159. It's going to go on forever and ever and ever. I gave you a 3 decimal place answer. Is it very accurate? It's okay, but how accurate is it in words? How accurate is this answer compared to what it's supposed to be? Anybody? How many decimals are accurate, in other words?
2.
Just 2. Yeah. I mean, we only did a third degree Taylor polynomial. If I wanted greater accuracy, obviously more terms would have helped. So this is a fairly crude estimation, but you'd say, you know, It's not that bad. I did a third degree polynomial and I have something that's accurate to 2 decimals. But I said before, I want 10. I want 20. I want 100. I'd have to have a lot of terms before I could say that. Okay. So for this answer here, I want 10 decimals at least. But I don't even have an antiderivative. No, but we're going to do what we did on this one. We're going to treat it as a series because there's no other way. It turns out in the world of integration, of every conceivable integral that exists, not very many can actually be integrated. Think of the infinitely many ways you could just write cosine of function. There's an infinite number of functions you could write, but only cosines of constant multiples of x could you integrate immediately. Everything else would need a chain rule factor, which you don't have. So there's an infinite number of variations of the cosine that don't have antiderivatives, and only one of them that does, cosine kx. So what we're going to do is replace cosine x squared with its power series. So let's write what we know. We know that the cosine of x we know this. Okay, so if we know this, then what's the cosine of x squared? Well, this part's going to stay the same. What's going to go in this place? So the tweakage rules, that x goes right there. But now this is going to be an x squared. So technically what's going to go there? X squared to the 2n, which is what?
X to the 4n.
X to the 4n. By the way, I don't mind if you guys stay unmuted as long as you don't have like, a lawnmower running in the background or something, or you don't have your mom screaming at you, get your room clean. That happened yesterday. It was pretty funny. When grown-ups are being yelled at by mom, it's bad luck. All right, so if I replace this with this, how does that help me? Well, let's look at the antiderivative first. Forget the limits of integration just for a moment. Here's my question. True or false? What do you think? True or false? The integral of this is equal to the integral of this crazy looking thing.
True.
True, because we said that this is equal to this. But there's going to be a lot of, I have an infinite polynomial, I have to integrate it. That might take me a little while because there's an infinite number of terms I have to integrate. Actually, no, I only have to integrate one term because we know something about integrals. So don't we know that the integral of a sum is the sum of the integrals? We know this. So can I rewrite this as the sum of the integrals? The integral of a sum is the sum of the integrals. We know this. Oh, so I can do it like this. See, when n equals 1, I have a particular function. When n equals 2, I have a particular function. When n equals 10, I have a particular function. But rather than integrate each of those specific functions, I'm going to integrate one thing because right now I have an integral. Right now, x is the only variable. N is a constant in my integral. N is changing in the sum, but within the integral itself, n is a constant. I'm going to find the antiderivative of this. And I'm going to take the sum of the antiderivatives. So if the original problem, I'm going to do the integral of the sum, then I'm basically going to integrate each term one at a time. So that's just the sum of the antiderivatives. So we're actually going to do it like this. Now, remember, I'm only integrating the x. This is still constant. So now let me go and put the limits back in. So when I had 0 to 0.2, and by the way, why 0? Because this expansion of the cosine, remember, this is expanded about 0. right? It's not x minus c, it's just x to a power. So it was expanded about 0. And the way it works with the power series, if you want any degree of accuracy, you need to evaluate the power series near to the number you expanded it about. So if I wanted to evaluate the cosine at a really large value, then expanding about 0 is not practical. So if I want to evaluate it, again, I need to evaluate at really small numbers so that it's close to what this is expanded about 0, so I'm evaluating at numbers near 0. So here, 0, 0.2. So let's find the antiderivative of this. Well, what would the antiderivative look like? I'll throw this sum in here. I'm going to have to erase in a moment. Well, I'm only integrating x to the 4n. So that's going to be, I'm going to write the other stuff down again. It's not going anywhere. And the antiderivative of x to the 4n would be 1 over 4n plus 1 x to the 4n plus 1. All right, we're just increasing the exponent by 1. And then I'm going to take that quantity and evaluate it from 0 to 0.2. Oh, okay. I integrated the general term of the power series because I swapped the order. Again, the integral of a sum is the sum of the integrals. So whatever order you did it in, it cannot change the answer. So now all I got to do is evaluate this. So let me go ahead and erase. I'm going to erase this. I don't need this.
Professor, and you said because the n is a constant, essentially.
Within the integral, see, n is the only thing changing on the sum, but because I'm doing one integral at a time. So think of it this way. When n is 0, I put a 0 in for n. X is the only variable. I would then integrate that. Now let me put a 1 in for n.
Oh, sure.
Think of it like that. So
yeah.
Within the integral, n is a constant, x is the variable. That's why that's why I don't touch this in the integration. I only touch this.
Okay, that helps. Thank you.
I don't want to say it's a clever step because it's the rules of integration, but it's what allows me to do an infinite sum is I only have to actually integrate the general term. The same thing would be true if I wanted to take the derivative. Because the derivative of a sum is the sum of the derivatives, I'd only have to differentiate one thing and then take the sum of all those forms. That's one of the beauties of power series is you can do this form of manipulation, which heavy dose of it in Math 255. So now when I write this out, see, I've already integrated. When I evaluate this quantity at 0, won't it be 0? When I stick a 0 into x, that's going to be 0, isn't it? So I only have that. So now I have -1 to the n over 2n factorial, 1 over 4n plus 1. And now finally, I'm going to have 0.2 raised to the 4n plus 1 power. If I don't write anything else, I've just said this integral here, which we can't integrate, is equal to this power series over here. And by the way, this power series no longer has any variables. So the power series on the right now is equal to a number. And I know it's going to converge because that's the thing is the sine, the cosine, and the e, the interval of convergence, remember, was -infinity to infinity. They had no restrictions. Now, I still don't like the way that looks. Isn't 0.2 the same as 1/5? Might make it easier on me if I think of 0.2 as 1/5. I'm going to go ahead and erase this because I've got it up there. So if I think of that as 1/5, let me write it one more time then. Then this is going to be, let me just write one big quotient. Right now, my numerator is just -1 to the n. My denominator's got a 2n factorial. It's got a 4n plus 1. And if that's 1/5, then it's going to be 5 to the 4n plus 1. Everybody see that? Because 1/5. Now, whatever this is, I'm saying it's equal to this. Now, in real life, you know what you do? You'd stick that on a computer and you'd have the computer add up. The computer can't add up an infinite number of values. Darn. Oh, but wait a minute. This is a convergent series. And to be a convergent series, we know the terms have to be getting small. wait a minute, but the harmonic, the terms get small. You're right. So they have to be getting small really fast. They have to be getting small so fast that I may not need that many terms. So what I have up here is the answer to the question. What I'd like to do next is let's just write out the first few terms. In fact, we're going to write out the first, we're going to go up to just 3. So let's do 0, 1, 2, and 3. Let's only write that much out. And you're going to love this. I just get all excited about this point. All right. When n is 0, what do I have? When n is 0, I have 1, 1, 1, 5 to the first power. So I have 1/5. That's n equals 0. Now, n equal 1, it's going to be a negative 1. So I'm going to put minus. When n is 1, I'd have 2 factorial times 5. When n is 1, I now have 5 to the 5th power. Ooh. Okay, so if you want to know, that's, let me write it like this. That's 1 over, I've already done the calculations, 31,250. By the way, if I stop right now and I don't do anything, I've only done the first 2 terms. I've only gone up to n equal 1, and I've got 1/5 minus. If I wrote nothing else, I have an answer right now, believe it or not, that is accurate to 1, 2, 3, 4, 5, 6. This, I have what the actual answer is. This right now is accurate to 6 decimal places. This, whatever this is, whatever this infinite sum produces, which is an infinitely long decimal, I'm guaranteeing you that if I stop right now, I have the first 6 decimal places exactly correctly, and I've only gone n equal 1. Could you imagine if I went n equal 1,000? All right, let's do a couple more terms. Now n is 2. So I have a 1. I have a 4 factorial. N is 2, so I'd have times 9. N is 2, so I'd then have times 5 to the 9th power. Okay, so that is, that's a really big number, by the way. That's 421,875,000. Right now, I have well over 10 decimal place accuracy. How do I know that? Because where this one was, look at how many more digits this one has. So all of the in between, I said this was 6 decimal places. This is now accurate to 10. None of the decimals in between have actually changed. They've stayed the same. Now let's go one more term. I know it's a minus because it's alternating. So n is 3. So I have 6 factorial times 13 times 5 raised to the 13th power. That's a really big number. This number, again, I needed computer software to do this calculation. My calculator is a little inadequate for this. Now, here's why this concept, this process works so beautifully. For something to converge, the terms have to be getting small. This one, the terms get really small really fast. My third term, my n equal 3 term, which technically is my 4th term. Look at your denominator, 3, 6, 9, 12. Your denominator's 14 places. So 1 over that means that I have at least 13 zeros before I get to the next decimal. That's why you're guaranteed accuracy to that. Now, if I do this whole calculation, when I only said this much, what I got was 1, 2, 3, sorry. So 1, 1, 2, 3, 6, 8. This was a terminating decimal that equaled exactly this. Now that I've increased this, I got a few more decimals. Now here's the beautiful thing. This is an infinite decimal. But I can absolutely, I used software. I can absolutely guarantee you this is what my cheap calculator produced. But right now, this, if I stop right now and I use my titanium, I can do more decimals. This number is already accurate to at least 13 decimals. If I do one more number, it'll be accurate, I believe, to 21 decimals. The next number, I'll be accurate to 30 decimal places. If I just go to n equal 5, the decimal it produces, the first 30 decimal places are exactly correct. Would you say that's kind of powerful? That's unbelievable for, I think, for most people to say, okay, can't find the antiderivative, so I converted it to a power series. This is absolutely equal to this. And then we wrote it, this cleaned it up a little like this. These are absolutely equal. But this is going to produce an infinitely long decimal. There's no closed form. I can't give you the answer, like it's square root of 2. It's not like that. But if I wrote out the first few terms, you realize how fast this converges. So this here is guaranteed 13 decimal place accuracy. Whoa. Does anybody have a question so far? We're going to do a few of these. This is the whole point of today, is why are we doing series in general? We do series in general for the problems that can't be integrated. That can't be integrated, but I still answered the question. And I answered the question with unbelievable accuracy. Now, in real life, you say, do you need that kind of accuracy? I don't know. If you've had chemistry, what type of decimal accuracy do you need in chemistry? Does anybody know? This is kind of a trick question. Chemistry. Think about electrons and things like that. What is the mass of an electron is on the order of what? Does anybody know?
10 to the negative 31? Or
not quite.
No,
think of when you have a mole of something, it's on the order of around 10 to the negative 23rd. You're close. I mean, it's absurd. So in other words, in chemistry, you're generally going to have 22 zeros before you ever get to a number when you're doing calculations of massive different things. So in chemistry, you better have really good decimal accuracy. If you got that many zeros before you get to your first non-zero number, you better have the ability to calculate a really long way. I mean, I think we agree with that. Now, you're in physics, often you're working with astronomical quantities, but you're also working with infinitesimal quantities when you're looking at their reciprocals. So often it's the case that, again, you need tremendous decimal accuracy. And when I mean accuracy, I don't mean that, oh, when I convert it to scientific notation. No, I mean, you're never going to get to the scientific notation answer. You actually have to have all of the zeros correct before you get to the non-zero numbers, or anything you report in scientific notation is going to be, not very meaningful, because you can't guarantee, and we want to guarantee. So now let's look at one from a binomial series. And the reason I know this is going to come from a binomial series is because I'm going to do this. Now, this is cheating a little bit because we can integrate this one. We actually can. How would I integrate this one? Does anybody remember? Forget the limits for a moment. How would I integrate this? And it wouldn't be entirely pleasant, but you could.
Trig sub?
Yeah, I just do a straight up trig sub. I'd let x be tan theta. This one, and I want to walk you through it because every now and then you say, wouldn't it be easier if I did the trig sub? You're absolutely correct. In fact, I want everybody in here on your own to do this problem from beginning to end. I'll set you up on the trig sub. I would want you to do it from beginning to end using the trig sub so that you can give me the actual closed form exact answer. Then you can compare it to the decimal that we're going to calculate. Okay. Hopefully that makes sense to you. So if I was just doing this problem, we would say let x be tan theta, then dx is secant squared theta d theta. Then this becomes, sorry, not 1 plus x squared, 1 plus tan squared to the 1/2. But isn't this just going to be secant theta? So what does my integral turn out to be? Actually, we can't finish this. My integral turns out to be what? The integral of secant theta. So this one actually wasn't that bad at all. This isn't a formula. A lot of people say, well, is that like inverse something? No. If it were 1 minus x squared, it would be inverse sine. But there's no 1 plus x squared under the root. Not like that. I would need an x on the outside for it to be inverse secant. So I got this. And therefore, it's going to be secant theta plus tan theta inside the log. Okay. And then finally, what would I do? We go back to our triangle. if x equals the tangent of theta, then I would want an x and a 1, so that the tangent of theta is x over 1, and then that would be 1 plus x squared. Aha, that looks exactly like what it's supposed to be. So I want to continue. I said you can do this on your own. I'll just go ahead and finish this off. So this is going to be equal to the natural log of the absolute value, the absolute value of, well, what's secant? Well, if cosine is this over this, then secant is this over this. So that would just be 1 plus x squared under the root plus tan. And then I'm evaluating that from 0 to 0.1. Okay. So when I do that, I'm going to get the natural log. Now at 0.1, this would be the square root of 1.01 plus 0.1. I can drop the absolute value. And now when I evaluate this at 0, this would be square root of 1 plus 0, which is 1. And we know that the log of 1 is 0. So this is the answer right here. Now let's do a decimal calculation, because we're going to put that off to the side so we have something to compare it to. Okay, so when I do the decimal calculation, so natural log so when I do this guy here, I get approximately, I'll put it up here. Approximately 0.099834078. That's what my calculator produces. Okay. So hopefully y'all have something like that. Now, 07. Yeah. All right. Now, let's do the power series approach. Now that we know this one, I want to compare it to the power series to show you how ridiculously fast it actually converges. So how do I do this as a power series? Well, this is a binomial series. So the binomial series, think of this as 1 plus x squared to the negative 1/2 power. So that's the k. And then that replaces the x. Remember, we did a problem like this last day where I did an x squared. Oh, you know what? I just realized something. Oh, I was doing the problem as an x squared. The actual notes I have, it's actually x cubed. But we'll continue doing it as an x squared. That's funny. I can't read my own writing. I actually chose a problem that are on the notes. I chose a problem with x cubed. I chose one that actually cannot be integrated. But let's continue on this path. So when I do this one, what is it going to be? K plus, or I'm sorry, 1 plus, and then it'd be that over 1 factorial x squared plus, and then it'd be -1/2, -3/2 over 2 factorial x squared squared. Okay, I'll do the first few terms plus -1/2, -3/2, -5/2 over 3 factorial x squared cubed. Now this is going to go forever. What I want to see is a pattern as soon as I can possibly see a pattern. Now you recognize I'm going to see the 1, 3, 5, 7, 9 pattern. That's pretty clear. It's also going to alternate. Okay, so what I want to do is the n. So clearly I'm going to have a -1 to the nth power. See 3 negatives when it's a cube here, 2 negatives when it's a squared. I'm going to have the 1, 3, 5 pattern. Okay, so if I said do n odd integers, then the last one would be 2n minus 1. Remember, when it was even, the last one would be 2n. What about the 2's? I'd have a 2 to the nth, and I also have the n factorial. And then I'd have times x squared to the n. And we'll replace that in a moment. Okay. Now, do you guys remember the substitution we came up with last day for that guy? Does anybody remember what the odd one was? It ended up being 2n factorial because I multiplied in between by 2, 4, 6, 8. So the bottom ends up being this again. So it's 2n squared n factorial squared, and then I have the x squared to the n. This is the nth term. So I can clean this up a little bit, and finally that becomes -1 to the n, 2n factorial. If you want to do this, 2 to the 2n, or you could write it as 4 to the n. It really doesn't matter. It might be easier to write 4 to the n, okay? And then n factorial squared. And that last thing would be x to the 2n. All right. Now, this is an infinite sum, but we just figured out what the nth term is. Now I can write it as a power series. And that was my goal. Let me go ahead and write it right here. This here is equal to the power series, n equals 0 to infinity, -1 to the nth power, 2n factorial, 4 to the n, n factorial squared, x to the 2n. These are equal. So therefore, this is going to be the integral of this. So that's the next thing we're going to write. Change pens on it. A lot of writing, I know. So I have the integral of an infinite sum. I want to make that into the sum, the infinite sum of the integrals. Because that's what I'm going to integrate. I'll rewrite that one more time. Now, the way I've got it written, the n's within the integral are constants. That's a constant. I'm only integrating that term right there. That's a cool thing. So when I do that, okay, I'm going to get -1 to the n, 2n factorial, 4 to the n, n factorial squared. I'm going to increase the exponent by 1. So 1 over 2n plus 1, x to the 2n plus 1, evaluate from 0 to 0.1. Now, 0.1 is the same as 1/10. When I evaluate this at 0, it's going to be 0. When I evaluate this at 0.1, it's going to be basically 1/10 raised to this power. That's a powerful statement. So I am going to go ahead and put it right here. I'm going to put this answer right there. This is equal to the sum. Now, my numerator is going to be a -1 to the n times a 2n factorial. My denominator is going to be the 4 to the n, n factorial squared, 2n plus 1, and finally, when I raise 1/10 to this power, that's 10 to the 2n plus 1. Now, you don't have to put very large values in for n to realize this is going to get really big really fast because factorials grow the fastest, but I've also got n to a very large power. This is equal to this, okay? We have no doubt. I just want to write the first couple of terms down like we did before. So if we said, all right, what's n equals 0? For n equals 0, I have what? +1, 0 factorial, that's a 1. When n is 0, that's a 1. That's a 1 squared. When n equals 0, that's a 1. And that's a 10. Okay, there's my first term. Okay. Next term, minus. Now n is a 1. On top, I have a 2 factorial. On the bottom, I'd have 4. N is a 1, so that's still a 1. N is a 1, so that's times 3. N is a 1, so that's times 10 cubed. Okay, I'm going to erase this now. So what I have so far is 1/10. I believe that would be minus 1 over 6,000. Okay, just for fun, let's stop for a moment just to see where we are in a decimal. I've only done n equals 0 and n equal 1. Well, if I take 1/10 and I subtract 1 over 6,000, interestingly enough, right now, what I have is equal to infinite repeating because I have thirds. Check this out. 1, 2, 3, 4, 5. Right now, I only wrote the first 2 terms down, and we already have 5 decimal place accuracy, and I've only written down 2 terms, n equals 0 and n equal 1. So let's not stop there, shall we? Let's at least write, at least one more term. So what's the next term going to be? Okay, n is 2, so I have a 4 factorial on top. N is 2, so that's 16. 2 factorial squared. N is 2, so that's a 5. N is 2, so that's 10 to the 5th power. Okay, so, oops, so 16 times 4 times 5. Okay, let me try this again. 24. There we go. So right now, this is, oh, I should put that up here. Sorry. So that leaves me a 3 on the top. And then that term is 3 over 4 million. So let's just stop right now. All right, what I have right now with just 3 terms, not bad. Look where we are now. We now have 1, 2, 3, 4, 5, 6, 7 decimal place accuracy. I don't differ until here. So if I go one more term, only one more term, because I'd really like to get all of those terms. Well, what's the next term going to be? When n is 3, that's going to be 6 factorial, 4 to the 3rd power. I'll just leave it like that. 3 factorial squared, that's 6 squared. N is 3, so times 7. N is 3, so times 10 to the 7th. I guarantee you if we throw this term in there, we're actually going to go about 2 decimal places past that one. Unbelievable. Now, I was able to integrate this one, yes. But what if I put any exponent other than a 2 on there? What if I put a 3, a 5, a 7? What if I put something else on there? Then we wouldn't have been able to integrate it. Okay, but I can still do this process. So what this process is basically, in simple terms, is I'm demonstrating that if I take something that cannot be integrated, but can easily be stated as a power series, then I simply integrate the power series. That's it. It's actually that simple. But the better part is that knowing it converges so absurdly fast, most of the time, you're not even interested in this. Let me show you what you're actually interested in. So let's do a different one. Let's suppose that my ultimate goal was something like this. I want to integrate, let's say, from 0 to 0.4, just randomly. And I want to do e to the, I don't know, x squared. Well, I can't integrate e to the x squared, and I want you to do this, but I want you to do this using the first, let's say, 4 terms of the power series. Now, you like this instruction better because I do not now have to integrate the entire general form of the power series. I just need to write down the first 4 terms of the power series, then I can integrate them. You'll find that's probably a little bit simpler in general to look at it that way. So I know that e to the x is this. Therefore, e to the x squared, and this is based on the quiz you just turned in today, I'm tweaking this. So this would be x squared to the n, or 1 over n factorial x to the 2n. Okay? I just want the first, I said the first 4 terms. That doesn't mean, that has nothing to do with the exponent. I just literally want the first 4 terms. So when n is 0, what would I have? I'd have 1, I have a 1, okay. When n is a 1, I'd have x squared. When n is a 2, I have 1 over 2 factorial, x to the 4th. And when n is a 3, I'd have 1 over 3 factorial, x to the 6th. So I'm going to say e to the x squared is asymptotic, not equal. E to the x squared equals the infinite sum. It's asymptotic to this. This is a 6th degree polynomial. I guarantee you, if you graph this 6th degree polynomial on your graphing calculator and you graph e to the x squared, they're going to look exactly the same for a little while. Maybe between -1 and 1 or between -2 and 2. But for a little while, they're going to look exactly the same. You won't be able to see a difference. And here's why that's so cool. If these essentially look the same when x is small, then the integral of this should look relatively the same as the integral of this. But the integral of this is trivial. So now I can say it like this. The integral of e to the x squared dx from 0 to 0.4, I'm going to estimate this is the whole point. The integral of this is going to be estimated with the integral of this. Now, what we did before was we found the entire infinite sum. Then we just ran off the first few terms, and that's totally cool. That's absolutely correct. But it's actually a little bit easier if I do this. I said, let's start by running off the first few terms, integrate them, and then evaluate them. So the antiderivative of this does not present a challenge at all. This is just going to be what? X plus a third x cubed plus a 10th x to the 5th plus 1 over 42 x to the 7th, and I'm evaluating that from 0 to 0.4. I am not interested in a rational number. I'm not interested in the fraction this produces because this is already an estimation. This is where I would go straight to a decimal. Okay, yeah, it's totally appropriate to give a fractional answer, but 0.4 raised to the 7th, you're going to have a really big denominator. It's overkill. So when I evaluate this, that is my decimal estimation of that integral. And that's actually where this is used probably the most because it's a very practical thing. And the nice thing is I can use powerful computer software just to see how accurate that is. Now, this is a little beyond us in this class, but it is actually possible, even using just the math we know in this class, it's possible to figure out exactly how many terms you need to guarantee a certain decimal accuracy. It has to do with something called the error. How far off is this estimation from the actual answer? I don't know exactly, but I can put an upper bound and say, I want my error to be less than, and then pick, 0.0000005. I want it to be less than some arbitrary small number. You can actually work backwards and say, okay, I will reach that on the 5th term or the 7th term or the 12th term. It's possible to do that. And all the textbooks actually have that in there. It's not entirely practical, but it's possible. So if I need to guarantee a certain number of decimal place accuracy, then I would predetermine how many terms I would need exactly, do that many terms, and then I'm done. Okay, this is where I wanted to get to today. Some crazy wild stuff.